尬了。那所以到底应该在哪里？
它最多投的就是这个黑色的这个场景。
对呀，所以我刚刚是变成跟它黑色一
因为
样的，
它只卡到这下面，下面就看不到。
好吧，先这样试试看。
它只能这么办。
好。Okay, sorry for the technical difficulties. So in fact, a lot of things are fastly evolving and changing. So we are trying to get ready in case we have to move everything online. Okay, so today I'm going to, I hope the live streaming is working. And in general, the TA will post the link to the live stream as soon as they test it okay. And so in case there is any change to the class format, you will be able to view everything online. Okay, so hopefully we are ready for the rest of the semester. But for everyone here, the most important thing is to join the Facebook group if you haven't done so, because we will be using the Facebook group as a primary media for announcements. Okay, and so join the group, and if you have any questions, you should be able to post directly on the Facebook group. Yeah, so I need to get closer. So I'm a bit afraid of the mic, because today, I don't know if you've seen the news, NBA is suspending all games for the rest of the season because one of their star players is confirmed of the coronavirus. And one reason he got, I don't know if that's the real transmission path, but he was kind of protesting that everybody is so scared. And so he tried to, play with the mic. So, so we did not disinfect the mic. So that's why I'm sorry for wearing the mask today. But to some extent, I'm watching this coronavirus outbreak partly as a research problem. Okay, I'm not a doctor, and we are not going to be the one that's going to invent the the drugs or the test kits. But however, when you look at all the numbers, there are things that are interesting for computer scientists, in particular for AI people, to think about what are the different things that you may be able to do in this time. So if you haven't watched the news, you should know that today the World Health Organization officially announced that it's a global pandemic, even though everybody has been saying that, but now it's official. And I have two boys. One is working in Silicon Valley at Google, and they have been working from home since Monday. My second boy is in college, and yesterday they announced that everything through spring semester will be done online. So in the U.S., I think it's a lot of things are changing.
所以你声音没有收到，那狗狗声音要打开，有一个音讯输入的。
So I need to configure the sound.
再加那个
这里是要加哦，声音也在这里加。
看到 audio input 这个是这个。
哦，这个，对，所以这个下次应该摆这边。
哇，这触点特棒。
哦，好，所以等一下看看有没有声音。
好，
好，so hopefully. Okay. So, to some extent, I think it's actually maybe an opportunity for the university to really start pushing everything online. And I think NTU is not as ready to do that as some of the elite colleges like Stanford and Harvard. Harvard a few days ago announced everything moving online and all the students need to move out of their dorms in 5 days. Okay, so it's drastic. So that's why I'm not trying to scare you, I'm trying to ask everybody to get ready. Okay, so a few things. For the lectures, we are still trying to do it here, but in case anything gets more serious, we may move everything online. And even with the TA sessions, it may be conducted online as well. So try to get used to asking questions through emails or through the Facebook page. On the other hand, I understand that everybody, is here as a student, so your primary job is to try to learn and try to study. And in particular, you try to learn about AI. But on the other hand, with something going on and changing so rapidly, it may be hard to focus. So I decided that some of the students were asking about term projects, and I think it may be time for you to actually start thinking about term projects. And the overall theme for the term project will be AI for surviving the pandemic. So you can think about all kinds of ways that we may use AI technology in this part to help with some part of your life. Okay, so maybe some people were using some app to find the facial mask. And I think today we started rolling out the facial mask 2.0. And the governor was talking about they were using big data and everything in trying to analyze the demand and supply. So in fact, anytime when you have the opportunity to collect large amounts of data, there is the opportunity for applying the current, I would say the current groups of AI technology, which is called the data-driven AI. Okay, as I mentioned, we will actually start talking about model-driven AI, but model-driven and data-driven are very different approach, but I think the current trend is that they need to work together, okay? But with data, you may start thinking about this. So in fact, some people are very fast. Everybody knows last week there was this big spike in South Korea. So they've already released a data set of the cases in South Korea on Kaggle. And at this point, the data is mostly demographic and geographical data. So in a sense, they are trying to predict where the outbreak is going to be and where are the hot zones versus places where they're relatively calm. So to some extent, if you need to survive, you need to find places that are safer. How do you do that? Okay? Well, it's probably not a good idea just to go to places that do not have cases today, because you need to be able to predict where the cases are going to grow in the next few days or in the next few months. Okay? So those are the kind of data that you may have to deal with. The other thing is that, in fact, we have a speaker from Canada. Well, he is already in Taipei, so I do not worry that he would be quarantined. And So there will be an interesting talk. He will talk about censored contagion, how information on the coronavirus is managed on Chinese social media. Okay, so this is kind of how the information can be easily manipulated and give people kind of a designed idea governed by people who has the power. Okay, so it will be an interesting talk for everyone who might be interested in related issues. And in general, there is this big topic of so-called detecting fake news and detecting news that are not truthful or that are exaggerated or that may be misleading. Okay, there are many different types of information that may give you the wrong idea, and how do you detect them? So there are many different things that you may think about. Or how do you identify what should you stock up if you ever have to? You know, maybe not toilet papers, but what do you need if you need to be prepared for the next few months in case things got worse? Everybody has to be limited in terms of your mobility. What parts of your life will be affected may be based on some kind of model that you understand about people's life. Okay, so I hope I'm not trying to push everybody to think about the virus outbreak, but on the other hand, it's important that you understand what's involved. Okay, and so in fact, I realized that there was a picture I wanted to include, but I did not. I just realized. Give me a second. Any question while I'm trying to get the picture? No question? So how many people are actually living in the university dorms right now? Okay, so quite a few. Okay, so be careful because the dorm rooms are usually the, clusters where the regular seasonal flus got spread very quickly over there, but you just got to be careful. So where is my picture? Okay, so there are some important advice for everyone. So wash your hands often, avoid touching face, and cough into your sleep. The last one is intended as a joke, but it's also related to the fact that when you are deciding on what information is true or false, you probably need to identify the source. You should probably understand where you are getting the information if it's from a credible source. But then how do you decide if anything is credible or not? Can be a AI issue. Okay? So in fact, I talked about before all these fake news, we were using AI to do spam filtering. And when we do spam filtering, we look at not just the title or the keywords or the content analysis, but also where the information is coming from. Okay? So there are many things that are quite similar, but maybe extended or even more complex to deal with. Okay, so that's what I want to say before I start the content of the lecture. Any questions? Last week we started the overall introduction, and this week I'm going to rush very fast through chapter 2 and 3. Some of you are getting the books, and some of you may be using the book's digital copy or older version, a borrowed book. But you will see the book is quite substantial, and I do recommend people browse through the content. I talked to the author about the new edition, it was mostly additional materials. Okay, so the first part of the content should be relatively stable. Okay, so you're not going to waste too much time if you think, oh, this is going to be an old edition. What, should I read it? I think my general suggestion is yes, you still should read it. Okay, so for chapter 2, I'm going to rush it through relatively quickly because to some extent this chapter is the one that may be a little bit old, but on the other hand, the basic framework is still pretty much the same. But the fact that it's old is not that they are no longer true, but rather it's become so common that most people are already familiar with the ideas. Okay? So the idea is called intelligent agents. So in fact, last time I talked about the different definitions for AI, and the intelligent agents approach is the one where we try to decide whether something is intelligent based on the behavior rather than the thinking. And we decide whether something is intelligent using rationality as a guideline rather than a logical truth or falsity. Okay? With the rationality, I think the key difference with the truth or false is really we take into account the fact that there are limitations in terms of our sensing capability, our cognitive capability, and our action capability. Okay? So to some extent, given the same set of environment, same set of input, every one of you may be making or reaching a different conclusion. But each of the conclusion may all be very rational, okay? So sometimes with the rational agents or intelligent agents idea, we do want to kind of de-emphasize the fact that they are absolute truth or falsity, okay? Because sometimes it's really depending on the computational resources and hardware, software capabilities that you may have. But the overall view is very simple because this is all it is. Okay, an agent's view, simply say every agent, every intelligent agent is an entity that's constantly interacting with its environment through input and output. With the computer scientists, you are familiar with the notion of input and output. I think the only difference is that the input may not necessarily be read from your program. Okay, it can be coming from your sensors, it can be coming through natural language dialogue, or any other kind of information that can be taken in. And actuators can be even informational, or it could be physical. Okay? I usually like to use this simple example. Last time I mentioned about Nest. How many people have seen it or have used it? Okay, only a couple. How many people have used a thermostat at all? Okay? So to some extent, every student in this building, there is a thermostat inside each room. But it's funny because whenever I ask students, I realize that most people never try to control the temperature or never try to make adjustment. Partly because most people do not understand how to, do the right control. And even though it's such a simple device, okay? So with Nest, it's a very simple design. It's just a circular thing and you can turn. Well, of course, you can click to call out many different functions. But the basic function is simply turning the knob to give you the temperature that you want. Okay, so if you think the temperature is too cold, you turn it up. If you think it's too hot, then you turn it down. And the idea is that the Nest thermostat will learn your behavior in terms of your schedule and your preferred temperature. So this is a simple agent where it's taking input through a few ways. So what are the input to Nest? Huh? The user input through the turning the knob, right? So the user input in terms of desired temperature of the user. Okay? So in fact, if you look at many of the thermostat in any room, that they usually have a desired temperature that you can adjust. Okay? And with the more complicated control, you can press it to bring out additional menus. You can set the schedule. So those are also input. So to some extent, Nest will decide whether it should turn on the heater or turn on the air conditioning or turn off or do nothing based on these inputs and the current understanding of the environment. So in fact, the environment data is also input to Nest because Nest also have a simple sensing to know the current temperature in its surroundings. Okay? I mentioned that Google bought Nest for 3.2 billion US dollars. And they actually developed the whole thing into something called Work with Nest. So I'm going to
Say you have a smart light bulb. It's smart because you can control it from your phone. You can turn it off or on. Maybe change the color. That's cool. But add more smart products around the house? And without Nest, getting them to work together practically requires an engineering degree. And what works with one phone might not work with another. Ugh, that's confusing. Shouldn't home automation make life easier? That's why Nest does things differently. You can control Nest products from most smartphones, but they also use sensors and algorithms to learn about you. They're saving energy in millions of homes around the world. They're keeping families safe. They can even let you know when something happens, without you having to program them. They also talk to each other. Like when Nest Protect senses carbon monoxide. Your Nest Learning thermostat can automatically turn off your furnace, which might be the culprit. Now with Works with Nest, other products around the house can work the same way. They can take what Nest knows and start doing new things they never could before. So that light bulb can help get your attention when Nest Protect senses smoke. Or help scare away intruders if Nest Cam senses someone lurking around. Your dryer can learn from Nest and automatically run the next load when energy demand is low, which could help save on your energy bill. And your door lock can let you know who's there, even if you aren't home to greet them. You probably already own something that works with Nest, and we're adding more every day. Just look for the Works with Nest badge. The more products you have in your home that connect to Nest, the more your home will start to take care of things for you, without you having to do a bunch of work. This is how a connected home should work. This is Works with Nest.
Okay, so I think in this particular video, it gives you a little bit more idea about what this simple device may be able to perform. And maybe I can ask, what are the output or the action that can be done by Nest? In addition to just adjusting the, like turning on or off the furnace or the heat, air conditioning. What else? It may send a message to change the color of the light. Okay. Alert in cases of intruder. So that also requires the ability to send out signals to another device and maybe activate another action. So you see, any agent can be seen as an agent that's taking input, making decisions, and producing an output. The output may trigger additional actions by other agents or other devices. Okay, but if we look at this particular agent, it should be relatively easy to think about. So to some extent, many things that AI is trying to do is simply design the decision process inside this particular agent. Okay? So we talked about humans. So in fact, this I should have a little bit like showing some of the content slowly, but because I want to rush it through, cockroach is an intelligent agent. Okay, some of you may not agree, but it is able to sense, make decisions, and act. Okay, a human, of course, a robot, or even a software like an operating system or some of the programs that you have done, they can be viewed as agents. And the idea of agents individually is very simple. But in the early days of AI, one of the pioneers named Martin Minsky, he was an MIT professor and one of the participants in the Dartmouth conference that gave birth to AI. So he has a famous book called The Society of Mind, and he talked about the idea of not just a single agent in achieving a lot of work. You know, like many people think about AI, you try to think about this AI needs to be able to do very complicated capabilities. But in Minsky's idea, he is talking about AI as not just a single agent, but a society of agents. So where many simpler things come together and their combined actions enable expressive and knowledgeable behavior. So I see an assistant as an intelligent machine composed of many agencies of agents, not an agent being an intelligent machine. Okay, so in fact, some of these philosophical points was an early motivation for the connectionist approach. Many of you may not have heard about this term, but the connectionist approach is the foundation for neural nets. Okay, because neural nets is mostly consists of the same units of nodes, and each node is very simple, but with a design of very complex network, you will be able to achieve many complex functions and capabilities. So as I often said, many of the ideas or the theory behind whatever modern AI is able to achieve has been proposed 50, 60 years ago. Okay, so some of these people, they really have the vision for how things may work. But back then, in the hardware side, they were not able to produce many tiny devices and connect everything. I still remember in the 80s, MIT produced something called a connection machine, which has about 128 nodes. And that was already like a supercomputer of the time. But for any of you who have worked with neural nets, you know how many nodes do you have. 128 is definitely not enough. So with 128 nodes, they were able to show something very simple like a dictionary lookup. Okay, so but it's very expensive. So that's one of the reasons why AI kind of went into the dark ages in the 80s, because even though the ideas were very good, but implementation and the realization was lagging behind. Okay, so it's good that we are finally catching up in terms of the hardware and software capabilities. So in the book, they started talking a very simple agent in terms of this simple formulation where you can think about the agent thinking or decision making as a function mapping. Okay, So the mapping is from the sequence of scenes that you have seen so far. So they call that a perception or the perceptual history of the agent. So an agent program is simply mapping perceptual history of the agent into the action for the current time. So you can think about an agent while we are still mostly talking about discrete decision-making agents. Of course, at some point, you may be able to extend this notion to continuous functions, but that would be a lot harder to talk about. Okay, so for now, we are thinking mostly in the discrete world. So an agent perceives, mapping the perception history into an action, that's the decision making, and then take the actions. Okay, so you can kind of continue this cycle continuously all the time. So in the book, they use a simple vacuum cleaner world. As you can see, this is not something practical. This is really help you to think in terms of conceptualization. So you imagine there are two rooms in the world, a very simple world, and each room may be dirty or not, and you are an intelligent agent trying to clean up everything in the world. How do you do that? Okay, and assuming the vacuum cleaner agent is able to perform four simple actions: moving to the left, moving to the right, or sucking things up, or do nothing. Okay, so can anybody design a simple program to clean up the whole world? I think everybody can do that in a few seconds, right? How do you do it? Nobody wants to talk. Too simple. Think about it, if you were the vacuum cleaner, how do you clean the room? You check if the room dirty or not. Uh-huh. 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 Okay. Okay, so I forgot to mention that if the perception of the vacuum agent is limited, in the sense that he can only sense if the current room is dirty or not. So how do you do? Right. So basically, the vacuum cleaner tries to, so there are two simultaneous goals that it tries to achieve. One goal is trying to visit every room in some way, okay? The other goal is trying to suck up the dirt if he sees any, right? So if I put you in this random world, one thing that you could do is simply sense and suck up the dirt and move to the left or right depending on where you are, and again check and deciding whether to suck or not. Well, of course, there is a underlying kind of hidden assumption that checking is usually cheaper than sucking the dirt. Otherwise, you may just suck all the time, right? And that's actually the control program for iRobot's Roomba. The first edition of Roomba did that because it tries to invent a vacuum cleaner that's under 200 US dollars. Way back at the time when robots were costing like tens of thousands of almost $1 million at the time. And so I think at the time, 30 years ago, Germany has a vacuum robot on the train station to clean up the train station. but each of those machines costs like a large number of money, right? So when Ronnie Brooks trying to design the simple robot, he cannot do that. So he tries to make it very simple, and this is basically what he does. The robot just moves and sucks and moves and sucks, and he doesn't even have sensing. The first version, but then it has a sensing, and assuming sensing is cheaper than sucking up operation in terms of energy consumption, then maybe you check to decide if you need to suck up the dirt or not. Okay? There is also the assumption that the sucking action is actually working. So assuming you have a broken vacuum, every time you suck, some dirt actually comes out from the vacuum. Then maybe you will never be able to finish the job. Or imagining there might be a naughty girl or boy somewhere in the environment trying to mess up the environment, then you may not be able to finish the job either. Okay? So to some extent, when we design agents, we want to be very flexible in terms of what other entities exist in the world and what their intentions are, and whether something is working perfectly or not. We still want to be able to design something that will work. Okay? So think about it. Even though this is very simple, but there are many, many ways that this thing can break and may not achieve what it tries to do. But if this is a relatively simple world, then you could define a simple agent in terms of lookup table to define the actions that it will do by defining the perception and the action. So on the left-hand side is the percept, or just the initial perception, or at time 2, you have 2 perceptions. So it's usually called the percept sequence. And on the right side, depending on the sequence, you may have the actions that you define. So to some extent, many worlds are simple enough that you do not need to define the perceptual sequence infinitely long. Okay, maybe all the different percepts can be grouped into a finite set of possibilities. And that's usually this type of control can be defined in terms of finite state automata. Okay? So that can be easily done by a program, right? Okay? So those are sometimes called the reflex vacuum cleaner, where the robot simply look at the current situation and decide what to do. Okay? So the reflex agents are the most, like the easiest agent to design. So kind of back to our original definition of a rational agent is usually defined as an agent should strive to do the right thing based on what it can perceive and the actions it can perform. The right action is the one that will cause the agent to be most successful. So to some extent, when we talk about whether the agent is going to be successful or not, we need measurements of what, whether it's the right things or not. So what are the possible performance measures that you can define for such a simple world? Again? Yeah, it walk through all the rooms, A and B. Okay, so it kind of cover all the space. Any other suggestions for measuring the performance, how well the agent is performing? Well, of course, given that it's a vacuum cleaner, what's the most important thing for a vacuum cleaner? Anybody use a vacuum cleaner? If it cleans the room or not, right? So the how do you measure the cleanliness of the room? Is there a cleanliness meter somehow? Yeah, so in fact, people often measure by the amount of dirt that the robot is able to collect over time. Okay, so if you have a vacuum and often sucks up quite a bit of dirt, you think it's working well. Okay, so the amount of dirt cleaned up. What else? The time it needs to clean. So as I said, the first version of the Roomba actually did not have the notion of environment, no map. Because if you need a map, it's actually harder to use when you bring it home. You need to have a CAD program to give it the environment. So they try to make it simple so the Roomba will just move randomly. But if you do not design the random walk well, the robot may actually take a long time before getting through the entire room. But in the case of moving through the rooms, you may also have trouble trying to make sure it traverses through all the rooms if the environment is tricky. Okay? Many people have played with some kind of games like a dungeon type of games. You probably have a good idea of how to navigate through the rooms if you do not have the perception of the entire space. If you can only look at the room that you are in right now. Sometimes it takes some effort to try to remember. Okay, anything else? So maybe if you have to measure out the two things, you can measure out the time, measure out the square per time, and then you may have a penalty for square that are still dirty. Okay? And if you are energy conscious, you may measure the performance in terms of the energy consumed. You want to minimize the electricity consumed. Anything else? To many people in purchasing a vacuum cleaner, in fact, the noise level is actually important. So how noisy it is. So you may also want to minimize. So to some extent, even with such simple agents, you may need to think about how to define the objective function that you need to optimize in making the decisions. Okay? So when you specify the performance measure, usually it is a function from the state or the sequence of state that the agent traverses into a real number. Okay? So the control or the decision making of the agent is a function from perceptual history, sequence into action. But the idea of a performance measure is actually a function from the states to a real number, a real value. And a rational agent is simply defined as somebody who is trying to maximize its performance measures. And that's often called the rationality. Okay? So as I try to casually describe, rationality is different from omniscience, where you have the all-knowing, like a godlike perception and knowledge, where you may be able to know everything. But in fact, when we design an intelligent agent, we are often we are aware of the limitation in terms of the perceptions and the actions that you can take. Okay? So Rationality is also not clairvoyant because the action outcomes may not be as expected. Because when I say I want to pick up something, my arm may fail when I try to suck up the dirt. The dirt may not come up, and maybe some dirt may be coming out from my bag. Okay? But rationality is actually exploration, learning, and autonomy. And those are the things that kind of lays the foundation of many AI systems. So you want an AI system that is able to explore. It's not limited to things that you define the AI to do. So, with a lot of the news coverage and many people talk about AI, they often say AI is for doing the boring, repeated tasks. But I think that's not the right view of AI. The boring, repeated tasks are often can be done by automation, and that can be done with regular programs. You do not need AI. With AI, you want the agent to be able to explore new things, to learn, and to make decisions on their own. So autonomy means being able to make decisions rather than just taking orders, being programmed. Okay? So it's important that the agent is able to obtain new and useful information. The agent can learn and adapt. An agent can be determined by its own experience. Okay? I think especially the first point is often ignored by many people. Okay? Oftentimes people work with the data they are given. They forget that if you are a true intelligent agent, you should be able to think about what's missing. What additional information do I need? Okay? So in the book, they also define the task environment in terms of four aspects. I think I'm not going to spend a lot of time kind of just defining the terminology. We talk about performance measures, and we need to look at the environment. We talked about actuators and sensors. So this is the input, this is the output, and that's the kind of the function criteria, objective function for making decisions. So we haven't talked about environment. So we just need to look at something called, like in a very different examples. So in fact, these examples were given a long time ago. At the time, not many people have, seen a real self-driving car. But now, I think it's very likely that pretty soon you'll be able to take a self-driving taxi. Okay? So a self-driving taxi needs to be able to sense using cameras, sonar, speedometers. Well, I think what's missing, because these are old, so they never mention LiDARs. Okay? But the idea is that it takes multiple sensing to understand the environment. And the idea is that the self-driving taxi needs to be able to uh, control the direction, control the speed, control, whether it's going to signal or horn or communicate with other entities. Okay? So I think I'm not going to really go through all the details because this becomes very simple nowadays for people who have heard a lot about AI. So medical diagnosis is also a very popular idea for AI applications. Heart picking robot, which is a very common thing in so-called industrial automation robots, and maybe something like an interactive English tutor is also can be formulated as an agent. And usually when we talk about environment, we mention a few different dimensions, whether the environment is fully observable or not. Okay, as in the vacuum cleaner case, it's not fully observable. It's only partially. In the case of playing chess or Go, the environment is fully observable. Okay. In Taiwan, some of you played 象棋, which is fully observable, Chinese chess, but as a kid, you probably played I don't remember what would be the right name in Chinese. So oftentimes you play using the Chinese chess pieces, but you kind of cover it up and then you flip open to play, and that's partially observable. Okay, and some environments are deterministic and some are not. Okay, and so in fact, most real world environments are not deterministic, but a game or like a chess or Go, they are deterministic. Except that if you remember Harry Potter, there was a chess game inside Harry Potter. That game was not deterministic because it really depends on who kills who. Okay, so, but in the regular chess or Go, the rules is deterministically defined. And there's another idea called episodic, meaning that whether something is like a well-defined episode. So in a sense that when you make a decision, you want to know whether this decision is within a particular episode, or this is just a sequence of decisions that you have to make. Because if you have to make a sequence of decisions, then it may be very different from an episodic task. Okay, so to some extent, like when you play games, every game after you die is a new episode. Okay, whatever you have done in the previous game is not going to come into your current game. Like playing chess, every time you have start the game, it's a new episode. But with some many things may not be episodic. Okay, so to some extent, non-episodic problems are harder because you need to remember what you have done and you need to remember and learn from the experience. Okay, and with the environment, you often can define whether environment is static or dynamic, or whether the environment is discrete versus continuous, or whether it's a single agent versus multiple agents. Okay? So I think I pretty much just run through this table 2, and I just want to show you a few ideas of a simple agents. It's just the reflex agent is just like a table lookup. You send and you look at the table, pick the action, and you act. And if it's slightly more complicated, you may have a conditional action rules. In terms of a state machine, then you may have a state agent. So this is more like a simple, so these are graphics from the book. So I think it's, you don't really need to go through all the details because these are really, really just conceptual. Okay, so instead of having an internal model of the world, a simple reflex agent is simply taking in the information and making a decision based on the conditional action rules. But if you are slightly more complicated, you may need an internal model. And oftentimes, the internal model is thought in terms of an internal state. So your decision making becomes your input along with the state, and looking at the condition action rules, and then you make decision about the action. Okay? And if you are an agent with a goal, then your action may also depend on the goals. So that will make the decision making more complicated. With nowadays, nobody really think about the different parts. Everything is just a neural net. So, but the trouble is with the neural net, you will need a large number of input and output before the parameters are correct. But with a model-based agent, if you know exactly the right models and the right goals and the actions connection, then you may be able to get started without any examples, without any prior experience. So sometimes we compile past experience into something called a utility function. Because if you think about it, utility function is kind of your evaluation of whether something is good or bad. Okay? So for example, as a student, you may have to evaluate, what's the utility of reading the books? What's the utility of doing the homework? What's the utility of, playing video games? And you may have to associate different utilities with different outcomes. And then you use that to make decisions. So even in the old days, people started thinking about learning. Last week I mentioned that the oldest famous robot, Shaky the robot, in the 1968 and early 70s, they already have the learning capability built in. And so in the old days, they were kind of thinking about learning in terms of the system will make a decision, and there is a critic that will kind of give you feedback on how well you have done, and then you take that into consideration and change any future decisions that way. Okay? So if you think about it, many of the modern machine learning can still be framed in a similar format, except maybe some of these are defined in a particular structure or a particular function. So I'm going to show you a very old video, okay? Sometimes I think it's fun to look at old video. I hope it's not because I'm old, but I hope because it's important to understand what leads to the current invention. And maybe that will help you in shaping the future, okay? So in this very old video I'm going to show, it's done in 1987. I need to calculate how many years ago. Okay, so it's amazing to think, wow, things have really changed a lot since 1987. But it's interesting because it was a video done by Apple as a vision for what things are going to be 20 years from then. Okay, so they are trying to depict 2007. Now that we are already way ahead, but I do want you to look at the video and see which predictions become true, which are not there yet, and which are kind of different. Maybe they totally get wrong. Okay, so it's called Knowledge Navigator.
You have 3 messages. Your graduate research team in Guatemala, just checking in. Robert Jordan, a second semester junior, requesting a second extension on his term paper. And your mother reminding you about your father's surprise birthday party next Sunday. Today you have a faculty lunch at 12 o'clock. You need to take Kathy to the airport by 2. You have a lecture at 4:15 on deforestation in the Amazon rainforest. Right. Let me see the lecture notes from last semester. No, that's not enough. I need to review more recent literature. Pull up all the new articles I haven't read yet. Journal articles only? Fine. Your friend Jill Gilbert has published an article about deforestation in the Amazon and its effects on rainfall in the sub-Sahara. It also covers drought's effect on food production in Africa and increasing imports of food. Contact Jill. I'm sorry, she's not available right now. I left a message that you had called. Okay. Let's see. There's an article about 5 years ago, Dr. Flemson or something. He really disagreed with the direction of Jill's research. John Fleming of Uppsala University. He published in the Journal of Earth Science of July 20 of 2006. Yes, that's it. He was challenging Jill's projection of the amount of carbon dioxide being released to the atmosphere through deforestation. I'd like to recheck his figures. Here's the rate of deforestation he predicted. And what happened? He was really off. Give me the University Research Network. Show only universities with geography nodes. Show Brazil. Copy the last 30 years at this location at 1 month intervals. Excuse me. Jill Gilbert is calling back. Great. Put her through.
Hi, Mike. What's up?
Jill, thanks for getting back to me. Well, I guess that new grant of yours hasn't dampened your literary abilities. Rumor has it that you've just put out the definitive article on deforestation.
Aha. Is this one of your typical last-minute panics for lecture material?
No. That's not until, 4:15. Well, it's about the effects that reducing the size of the Amazon rainforest can have outside of Brazil. I was wondering, it's not really necessary, but,
Yes?
It would be great if you were available to make a few comments. Nothing formal. After my talk, you would come up on the big screen, discuss your article, and then answer some questions from the class.
And bail you out again? Well, I think I could squeeze that in. You know, I have a simulation that shows the spread of the Sahara over the last 20 years. Here, let me show you.
Nice. Very nice. I've got some maps of the Amazon area during the same time. Let's put these together.
Great. I'd like to have a copy of that for myself.
What happens if we bring down the logging rate to 100,000 acres per year? Interesting. I can definitely use this. Thanks for your time, Jill. I really appreciate it.
No problem. But next time I'm in Berkeley, you're buying the dinner.
Dinner, right.
See ya. 4:15.
Bye-bye. While you were busy, your mother called again to remind you to pick up the birthday cake. Fine. Print this article before I go. Now printing. Okay, I'm going to lunch now. If Kathy calls, tell her I'll be there at 2 o'clock. Also, find out if I can set up a meeting tomorrow morning with, Tom Lee. Enjoy your lunch. Hello, Professor Bradford is away at the moment. Would you like to leave a message?
Michael, this is your mother. I know that you're there. I'm just calling to remind you to call your sister and pick her.
Well, Apple still has the old logo. So you can see the age of this video. But I do want you to think about what if there is anything that you think is very surprising or different from the prediction that's happening right now, or anything that is not there yet. Okay. Anybody who wants to chime in? Or maybe we should take a break, and when we come back, we will talk a little bit more. Okay, I'll let you think about this video. Okay, so we will be back in 10 minutes. Okay, so let's come back, and well, I should ask if anybody has any comments about the previous video. No comment? Did Apple make a pretty good prediction? We are very far from having a general purpose AI that's as smart as an assistant. You know, he was able to understand which calls are important to interrupt the conversation and which calls are, can be avoided. And he's very good with getting the information. Remember, the professor was thinking about maybe 5 years ago, he didn't even get the last name right, but the agent was able to get the right paper for him. I don't think that's available now. Okay. It will be a very nice research tool that is available nowadays. But on the other hand, in terms of hardware software, you can see it's way underestimate how far we have come in terms of screen resolution, in terms of storage, and so on. Okay, so to some extent, I have to say in the past 30 years, hardware has exceeded expectations, but software is still lagging. Okay, so you guys need to, help to make many of the ideas become reality. So, in fact, as a tradition, many companies often push out these concept videos about their vision of the future. And Apple has been one of the companies that has been very good in terms of pushing out kind of far away vision. And I have to say, many companies are still doing that. So sometimes it's fun to look at what's there and trying to get some ideas, maybe for your research. Okay? But of course, some things look simple but actually hard, and some things look hard but actually simple. To some extent, what's difficult or easy for machines can be quite different from for people. Okay, we have very different capabilities. So here is another big project that also includes a lot of the AI ideas inside. It's called Project Oxygen. Okay, oxygen as in the air that you breathe in. And the idea is called the ubiquitous AI, okay, because oxygen is everywhere and you need it to survive. So they're thinking maybe AI or all these intelligent technology will be ubiquitous. This video was also done more than 20 years ago, and it's, sorry, I was in the wrong window. So I'll play a clip. So this is just one of the videos they produced in the project. So this video is not the overall view of the entire project, but if you Google, you will find many other clips. But I'm picking this because I think it's especially interesting for my perspective. Okay.
Let me show you an example of the Assist Sketch Understanding System in operation. I'll draw a simple mechanical device and show you that the computer understands what it is that I've drawn. I'll start by drawing a simple hill I'll anchor it to the background. I'll put a little cart on the hill, give it wheels, pin the wheels to the frame with some axles, and then indicate that I want gravity. And now if I'd drawn this on a piece of paper and shown it to you, you'd understand what it is that was about to happen. I want the computer to be able to understand what's going to happen as well. And I can simply push the run button, and it produces the expected simulation. Now, I'm going to run that again, and I want you to pay attention to how the car moves as it runs down the hill. You'll see that it wobbles just a little bit because I haven't drawn the axles in the center of the wheels. Now, one of the nice things about an online environment is we can have the advantage of having it feel like paper and yet be able to do things that are not possible to do on paper. For example, I can take this and decide that I don't have it in quite the right place, and what I'd really like to do is move it just a bit and put it over here. Then I'll run the simulation again with my new conditions. And finally, we'll go back there one more time. And this time what I'd like to do is make the simulation a little bit more interesting and a little bit more complicated. We'll add a speed bump and anchor it to the frame. And we'll add a pendulum. And now let's see what it is that our system is going to do in operation. It still manages to make it over the speed bump and head on down the hill. Now, let me try another device. This time, something a little more similar to the kind of thing that might happen in a real design environment. Here you see I've circled all of my previous drawings, and I'm just going to get rid of it by saying, scratch that out. And let's try a simple little marble game, the kind of thing that we might have in a real design environment. I'm going to draw a collection of boards for the marbles to run down. I'll anchor them to the background, put one more board down here, and let's give them a cup to fall into. And just to make it interesting, we'll anchor the cup with a couple of springs, put some marbles up here, okay, now let's see what this does. Oops, not quite. Let's go back to the drawing board, literally, and see if we can't fix things. Suppose we take this shelf and move it a little bit. And then let's take this shelf over here and move it a little bit. And now, let's try the device again. Still missed. One more shot at it. This time, let's try grabbing the cup, changing its location. All right, we've succeeded. Now what I wanted to show you is we have a design environment, the beginnings of a powerful design environment that allows a kind of natural and familiar style of interaction.
So do you have that with you now in your computer? Well, we have many very powerful simulations, but still, it's some of the tools are still not nearly as natural to use as what's shown in this demo video. Okay, and this is another visionary view of this is done by Microsoft. Almost, I don't remember the year, but it's almost 10 years ago. And I'll show you the video.
Over the next couple of decades, the way we work with computers and interact with them will change dramatically. Computation will be overlaid in new kinds of ways and present in our daily lives. One of our core projects where we're studying the future of human-computer interaction is called situated interaction. This project is looking at giving computers new kinds of reasoning abilities to understand the pace of conversation, how engagement between people occurs.
The Receptionist project is a specific instantiation of this long-term vision that we're pursuing. The parts that we're looking at have to do with how do you manage conversation, engagement, attention, floor, and grounding. So how do you relate all these different concepts and create a system that's able to engage in an interaction that's free-flowing, and follows the natural pace of human conversation.
Hi. My name is Laura, and today I'm here to help the receptionist with shuttle reservations. What's your name?
I'm Dan, and this is Eric.
Nice to meet you. Do you need a shuttle?
So what you'll see noticing is that the system is able to detect multiple participants in the scene. It's able to track their poses. Here it knows I'm oriented towards the system and Eric is oriented towards me. It's composing that with information from the microphone array, which tells us the direction that speech is coming from at any given moment. And with an analysis of the torsos of the different actors, basically of the clothing that we're wearing. And based on that, we infer a number of variables about the actor. Then we go one level up in this analysis and gather information about the tasks that are active here. So the system analyzes the relationships between the different actors and infers that here, most likely, Eric and I are in a group together and we're engaging as an active task to the system, and our current goal is to get a shuttle. We believe that it's a very good platform for doing that kind of work.
Which building are you going to?
I forget, where are we going?
I think it's Building 9.
You sure?
Yes.
So, you're going to 9, right?
Yes.
And this is for both of you, right?
Yes.
I'm making a shuttle reservation for Building 9 for 2 people. In case you want to correct anything, say or press start over.
So,
Okay.
Are you visiting someone?
Okay.
Yes.
So I think
I'll help you register in just a moment.
fabulous. We learn the most when we pick projects that are at the edge of doability. They're almost impossible, but we see a glimmer of the way to do something, and we pursue that terrain. And this is the best way we learn about the future.
Excuse me, sir.
Yes?
You will be on Shuttle 53. It should be here any second.
All right, thank you.
Bye-bye.
Bye.
In our work, we're also exploring the notions of complementarity between people and computing systems. People won't go away. They'll always be with us.
Hi, can I help you?
But we're trying to study the best way to use computers and people together.
There are several interesting things in this scenario. Is that the computer, of course, back then, facial recognition was not as good as what we are able to do nowadays, but they are able to recognize there was a person. So, but what's really interesting is that the computer was able to identify the 3 people it is seeing. There were 2 in a group, and another one is a separate guest. So, the 2 persons did not tell exactly that we need to go to building 9, the 2 of us, but the computer kind of figured that out on its own. Okay, that's actually something that looks simple, but very difficult to do. Any guess about how they actually identify which people are grouped together? Their proximity in terms of their physical shape, and also he mentioned about they are able to identify the torso orientation, so they are kind of facing each other, and there were conversations. But in fact, that's actually very hard. The computer is able to identify who is speaking, and they were talking, and then computer waited until they are done, and then without they're talking to the computer directly, the intelligent receptionist was able to get the instructions. I don't think AI in most situations is able to do that already. Okay, so most of the time when you talk to the voice assistants, you still need to wake up, right? You still need a wake word like Siri or Hey Google or Echo, and uh, so you still need a word to call the attention of the computer. Otherwise, the computer was not really paying attention, was not able to analyze the dialogue situation, the dynamics of the different conversations going on. There are only 3 people in the scene. Think about if you are in a cocktail party with many, many people. It will be extremely hard for AI, maybe there is an intelligent room, to understand who is talking to what. So, for example, in this, again, I'm using coronavirus as an example. So, I don't know if you have seen the news about there was one uh, conservative Republican donor that has been confirmed with the virus, and many people were kind of now they're on something called self-quarantine. So if you have an intelligent room inside the convention, you will be able to automatically identify who are the people who may be at risk. Okay, but at this point, we are kind of relying on the people who self-identify and self-discipline enough to say, oh, maybe I have to be careful. I need to stay home. Okay, so that creates additional burden on everyone, and also you need to understand people, although we are very smart, we are very flexible, people's memory is also very faulty and very moldable. Okay, there are many psychological studies that have shown that it's relatively easy to edit or modify a person's memory. Okay, so even when somebody said they remember something or they don't remember something, that can often be a mistake. Okay, they may not try to lie to you on purpose, but their memory is not perfect. Okay, so there are situations where we may want to have intelligence surveillance or monitoring of activities inside a particular setting. So, how many people know about IBM Watson? Heard about it? And how many of you actually have seen the game Jeopardy? Okay, because I found that has been a challenge to many people in Taiwan because they have not seen the game show, so they may not understand what's going on. But in so this competition was took place in 2010, 2011 during that time frame, and it took IBM many years to assemble a big team of more than 20 PhDs with expertise in computer science and linguistics and all kinds of language processing skills. And they try to digitize, put everything inside a big brain, the IBM brain, and they call it Watson. Why Watson? The name is actually the name of the founder of IBM. Okay, so I'll just play the video and then I'll explain.
I remember that morning going to the lab and I was thinking, this is it. This is the last Jeopardy game.
It became real to me when the music played and Johnny Gilbert said, from IBM Research in Yorktown Heights, New York, this is Jeopardy! And I just went,
This is Jeopardy! The IBM Challenge!
And here it is. One day. This is the culmination of all this work. To be honest with you, I was emotional. I just thought about all the genius and all the talent of these researchers. I mean, they changed their lives. They changed the way they work, which is not always easy. They made this thing happen.
You know, when you look at that stage, you see Ken and Brad and Watson, and there's 30 people standing behind Watson. And that's just the core team. There's a whole army of people that have helped make this happen.
Here we go.
Once we got into the game, it was nerve-wracking, frankly.
Brad, if you're ready, make your first choice.
Let's take alternate meanings for 200, Alex.
4-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
after the first clue of the game, which Brad won, I had just this horrible feeling at that moment that he was as good as everyone said he was, and he was just going to run the whole board on us.
Alternate meanings 400.
4-letter word for the iron fitting on the hoof of a horse or a card dealing box in a casino. Watson.
What is shoe?
You are right.
We actually took the lead. We were ahead of them, but then we started getting some questions wrong.
Watson.
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is chic?
No, sorry. Brad.
What is class?
Class, you got it. Watson.
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
A lot of people were feeling good because Watson held his own and, you know, was doing pretty well, but I wanted to be winning.
Too close for comfort. Ken, you're in third place. That means you go first in Double Jeopardy.
The Double Jeopardy round of the first game, I thought was phenomenal.
Watson went on a tear.
Watson.
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson.
What is narcolepsy?
You are right. And with that, you move to $36,681. Let's take a look at the category for Final Jeopardy. U.S. cities.
Final Jeopardy is hard for us. Those questions are tricky. They often involve putting two different pieces of information together from different places.
It involves what we think of as number of hops to the answer. So you have something missing in there that Jeopardy wants you to think of.
Here is the clue. Its largest airport is named for a World War II hero. Its second largest for a World War II battle.
To a human, I think that's a very hard question to get wrong. And I'm used to seeing all three players nail very easy questions. So I get it right, then Brad gets it right. Watson only gets it wrong, but he names a city that's not a U.S. city.
What is Toronto? With a lot of question marks.
Now people look at that and say, wait a second, you know, Toronto isn't even a U.S. city. Watson's not dealing with structured databases. It's trying to understand language. There are lots of cities in the United States named Toronto. The actual city in Canada also has a baseball team in the American League. Very often there are categories in Jeopardy, but the answers to the questions are not that type of thing that's named in the category. The Watson system knows that and says, yes, U.S. city might be part of answering this question, but there are other elements in this clue that must be considered.
Most importantly, the confidence for that answer was very low. It's definitely not a question that Watson would have buzzed in for if it had had the choice.
The illusion is that this computer's doing the same thing that a very good Jeopardy player would do. It's not. It's doing something sort of different that looks the same on the surface. And every so often you see the cracks.
And the wager, how much are you going to lose? Oh, you sneak. $947.
After the first game, we have a pretty good commanding lead, but we've seen enough Jeopardy to know that this is not a lockout.
Welcome to the deciding game in the IBM Challenge here on Jeopardy.
The second game was a whole other story.
We struggled some at the beginning.
Actors who direct for 1,000.
A Bronx Tale. Brad.
Who is Robert De Niro?
Correct.
That was an awful category because Watson got every single one right, but was just a little too slow.
Ken.
Who's Denzel Washington?
You got him.
Ken and Brad were getting the answer in a second.
Rocky 2, 3, and 4.
Brad.
It was Sylvester Stallone.
Correct.
Even with 2,800 cores, it took us 2.5 seconds or 3 seconds, and that just gives you a sense of how incredible the human brain is, how quickly it could understand the category, what's being asked, boom, and get the answer.
Who is Sean Penn?
Right.
Ken was doing very well, and the risk was Ken gets a daily double, bets big, gets it right, he's going to be well ahead, and then with that kind of lead going into Final Jeopardy, if he bets enough, he could end up winning the match.
A camel is a horse designed by this. Ken.
What's a committee?
Good.
Familiar sayings for 2000.
We got to find that last daily double. We got to find that last daily double.
I was nail biting. I mean, it was just intense because these guys were good.
Ken.
Who's the brain?
Brain, yes.
It was a crucial moment in the game. There was still a daily double on the board, and it was starting to become pretty clear that it was in the legal ease category. Let's go to legal ease for 1200.
This person is appointed by a testator to carry out the directions and requests in his will. Watson.
What is executor?
Right.
Same category, 1600.
Answer, daily double.
That was the moment when I knew it's over.
Our three players have made their wagers. The category is 19th century novelists, and here is the clue. William Wilkinson's An Account of the Principalities of Wallachia and Moldavia inspired this author's most famous novel.
What Watson wants to do then is preserve the lead, not take a big risk, especially with Final Jeopardy, because just like for humans, Final Jeopardy is hard for Watson.
Like we knew we probably were going to win, but what if we didn't turn on the system to play in tournament mode? What if we did the math wrong for some reason and lost by $1 instead of won by $1?
I wanted to wait till we see the final scores there because you don't know if something might surprise you.
You came up with what? Who is Bram Stoker? You are correct. Over to Ken Jennings now. And we find who is Stoker? I, for one, welcome our new computer overlord. Now we come to Watson. Who is Bram Stoker? And the wager? Hello, 17,973, and a two-day total of 77,147.
Stand up, stand up, stand up.
At that moment, it was just, wow, we won. It was just so much happiness.
Jennifer has been on the team from the beginning, and she's so proud of the accomplishment. And she was crying, and she hugged me, and she said, "Thank you." And I said, "Thank you." It was these people who they did everything. I mean, no matter what I asked, no matter what I said to push on, they did it.
Amazing 4 years, huh?
I think I'm going to stop here. And so, for some of you who do not understand Jeopardy, it's a game where there are many different squares that you can pick, and each square is kind of a question, a kind of description of the question, of the answer. But then the player needs to be able to answer give the answer in the form of a question. Okay, so they always have to say what is or who is. Okay, so they are kind of a twisted way of trying to test you. But it's basically something called the trivia, Q&A. Okay, so a question and answer. So with the trivia, a lot of them can be done by more like information retrieval. So basically, when Watson swallow a huge amount of information, all the novels, all the movies, all the cities, countries, all the factual information, Watson is able to answer most of the questions easily. Although you can see in the video, they show that Watson also calculates something called the certainty. When he is sure about his answer, the certainty is high, and when he's not sure about the answer, the certainty is low. But with some of the questions you see, that Watson also needs to be able to combine a few pieces of information to derive at the correct answer. So, in fact, those are the things that is not easily done with information retrieval. So there is some kind of reasoning involved, okay? But I think in one of the example of the U.S. city, Watson actually got the answer wrong in a kind of the kind of wrong answer that would not be given by a human because he gives a city that's not even in the U.S. Okay, but so to some extent we decided kind of we can observe that Watson does not have common sense, even though it has a lot of trivial knowledge. So the two human competitors, one is the all-time champion for the longest winning champion, like the most number of consecutive games. And the other is the highest award winner. Okay, so he has won the most prize money from this game. So the two are really, really good. Okay, so you can see that Watson needs to be able to retrieve information, piece information together, and estimate the certainty, and also being able to calculate the bet. For the final jeopardy, it needs to be able to decide how much he is going to wager. And also in the strategy of picking the problems, because he may understand that he is better with a particular category, and maybe which square he should pick, whether he should pick the higher price or lower price. So there are multiple decisions that's going on inside Watson. So in 2011, Watson won this game. In fact, it was a little bit unfair competition. Again, I always think when computers playing against humans, it's unfair. Those two human beings are just by themselves. They do not have any support, anything, any help. They are just there on the stage. And did you hear about what Watson is? What kind of computer is Watson, behind Watson? It's in the video, okay? It runs on 2,800 cores. That's a big cluster of CPUs. And you see all those people who are so excited. As I said, they have more than 20 full-time researchers working for more than 3-4 years on the project. And there are also, dozens or more data entry interns entering all the information into the computer. So even though Watson's the computer won, I still think humans are smarter. Okay, because it's like a one brain versus 2,800 cores, and plus 20 plus human brains. Okay, behind. Okay, but on the other hand, it's an interesting win because these competitions are hard. If you have a chance to watch the game, I used to enjoy watching them, but I always feel frustrated because I cannot answer most of the questions. Okay, it's hard. Okay, it's hard for typical people unless you practice the trivia. Okay, try to memorize many things. And so after this win, sort of like when IBM showed that they were able to defeat human chess players, they started selling their supercomputer. For this particular project, they tried to, this is a big media event. In fact, even though it looks like the Jeopardy stage, it's not at the regular stage. They were shooting everything at IBM. So they actually put the whole thing inside IBM. That's another trick because, the computer is a huge super clusters, and they don't want to take the risk of, communication error. Okay, so everything is on site. Okay, and they are also slightly deceiving because Watson does not really know how to read from the screen. Watson's problem was typed into Watson simultaneously. When the problem is shown, the data in terms of the language symbols was piped into Watson. Okay, so it's not really as magical as you saw in the video, okay, because Watson was not able to read at the time. Okay, I think nowadays reading is not no longer an issue, but then they may need an additional computer just to run the vision part, okay, and they need an extra CPU to run the question answering part, okay. So that's, but I think my point of showing these videos, because they kind of come in like 10 different, like every 10 years, you see the technology push forward, okay? In the IBM case with Watson, they decided that they are going to sell this not just for the hardware, but for the knowledge base. And in particular, they apply this technology to medical diagnosis and medical cancer therapy recommendation and so on. Okay, so so there was kind of a big commercial activities afterwards. Unfortunately, that team has since been, disbanded. Okay, it no longer exists. IBM is no longer selling Watson as is because it was a very expensive product and very expensive, very difficult to deploy. And so to some extent, it gives some vision and hope of what computer can do, but we are not quite there yet. Okay, there are still many problems that needs to be solved. Okay, so I think that kind of conclude my introduction for agents, and I think I'm going to take a short break, and I will show you. I will move on to chapter 3. That's when we start talking about problem solving and defining something called the search space. Okay, and but before then, I think we will. Give out the authorization code online by emails. So for people who have completed assignment 0 and submitted on time, you should be receiving the authorization code online. Okay, I mean in your email. And so I think just to get some idea, how many people here are originally enrolled in the class? Raise your hand. Okay, so how many people did not enroll successfully but submitted assignment 0? Raise your hand. That's a much smaller number than you thought. Okay, and so how many people who are here but who has not enrolled and has not done assignment 0? Raise your hand. So only one. Okay, so we can talk about authorization. Hold on. Okay, so before we take the short break, I think I'm going to have a really short break so that we can come back for the chapter 3. Any questions? I, I think I do hope that you do not just watch the video passively. Try to think about what's interesting inside and what's not quite there. And those are the parts that we may want to be able to crack, okay? Because as you see, for many people working with AI, they always have this grand vision. And even now, a lot of people have grand vision for AI. Many people are talking about using AI to solve the coronavirus problem. I think that makes me scared, even though I was trying to ask you to think about what can we do as data scientists plus AI people. There are many things that we could do, but AI alone is not going to solve the coronavirus problem. It may help people live better with the understanding that this thing may be here to stay, okay? And so we take a short break and we will come back for for chapter 3. Okay, thank you.